The last of our topics in our Chapter 3 called Chemical Reactions. Reactions involve chemical changes, and I know in our first meeting together we talked about chemical changes versus physical changes. Chemical changes, those things that produce new substances, can be written in a shorthand chemical sentence known as a chemical reaction. We understand that the initial ingredients, those things that we begin with, are called reactants, and they go on to form products. The original substances forming new products. Reactants go to products. Reactants yield products, that arrow representing the chemical change. So when elements react or compounds react, we break bonds, rearrange them, and form new substances known as products. These equations are just shorthand ways of describing a chemical reaction. The information that's provided to us, well, we know the formulas for the reactants and the products. We know the states of the reactants and products. Are they solids, liquid, gases? Are they aqueous, which means dissolved in water? We know the relative numbers of reactants and products, called coefficients, telling us how many of each. And that can be used to determine the weights of reactants and the products. Knowing the law of conservation of mass, we know the mass of reactants must match the mass of the product simply because we can't destroy nor create matter. An example of a chemical reaction, a combustion pattern. Now we talked about combustion a moment ago when we were looking at chemical analysis from combustion. Combustion, when we take a hydrocarbon, burn it in oxygen, and out comes carbon dioxide and water. What are some of the things that we notice about this chemical sentence? Well, we see some chemicals on the left, separated by an arrow that's on the right. The term reactants denote those things to the left of the arrow, and the term products denote those things to the right of the arrow. Methane is natural gas. It heats our homes, perhaps lights your stove, runs your your dryer, your furnace. Methane, natural gas, is CH4. As a gas, the little g is representing its state of matter. When it burns, it uses or consumes oxygen. Now oxygen, if you remember, horses need oats for clear brown eyes. That funny little sentence to remember that oxygen is a diatomic element. In nature, it's found as O2, and it's in a gaseous form. When those two reactants collide and bonds break and atoms rearrange, we form two new products, carbon dioxide as a gas and water vapor. So reactants go to products, and we're getting some good information. These coefficients, the large numbers telling us quantities, say 1 molecule of CH4 gas combines with 1 molecule of oxygen gas to make a molecule of carbon dioxide and a molecule of water gas, called steam typically. Visually, just on a molecular level, this is a representation. Methane, CH4, got a carbon in the center and 4 H's attached to it. We have a diatomic element, oxygen, so see how those two O's are bonded together. Those elements rearrange to make carbon dioxide and water. Now visually, what do you see about the number of atoms of each element on the left and the right side? Well, I notice the carbon atom is represented correctly. There's 1 C. But on the left I count 4 hydrogen atoms, and on the right I only see 2. On the left I say 2 oxygen atoms, and on the right I count 3. This equation is not yet balanced. The number of each element does not add up on the left and the right side. We are not following the law of conservation of mass. This term is called a skeleton. Everything in this equation, reactants and products, is written correctly. We just don't have it balanced yet. So we start to go to work, and assuming that all reactants have to combine to produce the product, we're going to need some coefficients. To show that this reaction does obey the law of conservation of mass, we start placing coefficients in front of the elements or in front of the reactants and products to show an equal number of every atom. So take a look. By placing a big number called a coefficient in front of the oxygen, we double the number of oxygens. I now get a total of 4 O's. And if we double the number of waters by placing a coefficient of 2, we've got 4 H's and 2 oxygens for a total of 4 on the right. If you count the number and the kind of each element, it indeed matches from the left to the right side. We've balanced the equation by placing coefficients. Each side shows 1 carbon, 4 hydrogens, and 4 oxygens. A balanced equation that obeys the law of conservation of mass. So methane and oxygen are called reactants. Carbon dioxide and water are called the products. The little g after the formula tells us the state of the chemical, stands for the gaseous form. They're all gases in this particular example. And the number in front of each substance tells us the number of those molecules. Those are called coefficients. We have a 1 to 2 to 1 to 2 coefficient ratio. And this equation is balanced, simply meaning that there are equal numbers of atoms of each element on both sides of our equation. To obtain the number of atoms of an element, we simply multiply the subscript by the coefficient. 1 carbon, 4 H's, and 4 O's on both sides of our arrow. We can spot check chemical equations to balance them. Sometimes I use a T-chart, left side, right side, and count up the number of elements on both sides until I can guarantee myself they indeed match. Here are some other symbols that we see in chemical sentences. Symbols used to indicate the states of matter: little g for gas, an L represents a liquid, and an S for solid. AQ means aqueous or aqueous, your choice, dissolved in water, a solution. Salt water, NaCl, little AQs, dissolved in water. If I'm heating, we'll see a triangle placed over the arrow. Zapping it with light shows this is a physics quantity, hv for Planck's constant and velocity. Shock or electricity, sometimes I see a lightning bolt for electricity. These are just little adjectives we're adding to our chemical sentences. If we're asked to write a balanced equation for a combustion of butane, that's Bic lighter fluid is butane, C4H10. The skeleton would say to add oxygen, out comes carbon dioxide and water. Now a combustion pattern, I like to balance C's, then H's, then O's. C's will balance by placing a 4 in front of carbon dioxide. H's will balance next by placing a 5 in front of the water. Leave the O's for last and see what we get. Now I notice here when I place a 4 in front of carbon dioxide and a 5 in front of water, I get an odd number of oxygens. There's a total of 13 on the right, and there's no way I can balance O2, an even number, to make it an odd number. So I'm not allowed a fraction. 13 halves to give a total of 13 wouldn't work. We're not allowed to leave it as a fraction, but what we can do is double everything that we've learned so far. 2 units of C4H10 with 13 oxygens gives us 8 carbon dioxides and 10 waters. When we're balancing a combustion, get your carbons working first, followed by your hydrogens, and leave your O's for last. C's, then H's, then O's. Then, if you run into an odd number problem, as this example showed, go back and double everything, and the odd number turns even, and it will work very nicely. Here's a practice. Aluminum metal, Al solid, reacts with air, and that's the oxygen gas, diatomic oxygen gas, produces a powdery compound of aluminum oxide. Now consider charges. Aluminum oxide is a binary ionic compound. Al with its +3, O with its -2. Working those words into an ionic compound formula, we have to crisscross charges. Al +3 with O -2 becomes electrically balanced with the formula of Al2O3. This is a great skeleton, but it's not balanced. 1 aluminum on the left, 2 on the right. 2 oxygens on the left, but there's 3 on the right. What set of coefficients will work to balance that equation? Well, a 4 to 3 to 2. 3 oxygens on the right and 2 on the left are going to have to turn into 6s to get them to balance. To turn those into 6s, we place a 3 in front of O2 on the left side and 2 in front of the aluminum oxide on the right. Backing up to the original aluminum, we place a 4. We've now created a balanced chemical equation of aluminum metal combining with oxygen to form aluminum oxide. If acetic acid, HC2H3O2, now hear this acid review. Ic came from 8. I do not hear a prefix hydro, so I know it's an oxyacid. I pull out my polyatomic ion chart. Ic came from 8. Find acetate. First column, not too far down in the first column of your polyatomic, you find acetate. Hydrogen is always the first name for an acid. It's a +1. Acetate is a -1. Acetic acid, HC2H3O2. Reacts with is the plus sign that separates the metal aluminum. Out comes aqueous aluminum acetate and hydrogen gas. Now remember, we need a skeleton first. If we make a mistake with subscripts, chances are our equations will never balance. Aluminum acetate. Aluminum is a +3 when it hooks to make a compound. And acetate is the polyatomic ion that carries a -1 charge. We need 3 groups of that -1. See how we place that polyatomic inside of a parenthesis to take 3 groups of acetate. We read that as AlC2H3O2 taken 3 times, and we show that it's in an aqueous form. Hydrogen gas. Hydrogen is one of the lucky 7 diatomic molecules. It's that funny sentence, horses need oats for clear brown eyes. Those 7 elements must be written in diatomic form. Here's our skeleton. Notice that we have a polyatomic ion on the left, acetate, that appears unchanged on the right. Instead of counting C's and H's and O's individually, count that as a group of atoms acting as a unit carrying a charge. There's 3 acetates on the right and 1 on the left. There's 2 hydrogens on the right and 1 on the left, the H+, the beginning hydrogen of our acid. Count it alone, H+ and C2H3O2, 2 separate ions. I'm just counting them as 2 things. When we end up balancing, we end with 2 aluminums plus 6 acetic acids generates 2 aluminum acetates and 3 hydrogens. Tabulate the number we have. We have a total of 6 H's and 6 acetates, C2H3O2 as a unit, and 2 aluminums on both sides. Our equation balances with a 2 to 6, too fast, a 2 to 6, I'm sorry, I gotta back up. Aluminum acetate with a +3 hooking to a -1 charge. There it is, sorry. 2 to 6 to 2 to 3. This is the last slide of our lesson. We will not be going into the organic chemistry at this time. It's pushed forward into the chapter 20 much later in our journey. So at this point, you're going to be practicing balancing equations and really just starting to look at each individual element and make sure that it appears the same number as the left side on the reactants and the right side of the products. Good work this week in filling out your notepad, and I'll be collecting these and kind of awarding points for completeness and correctness. You should begin your assignment on the masteringchemistry.com homework site. Don't forget your quiz from the previous week as well on the Mastering Chem website. See you soon at class. Have a good week.